So lecture 9 from calculus. Again, the midterm is in 2 weeks, 2 weeks from Wednesday, in person in Gillette Hall, 11 o'clock. Any questions about anything we've done so far in calculus or in general in the mathematical world? So I hope everyone is up to date, that is working continuously online doing the exercises. And we will continue with lectures. So let me start with a couple of problems, and then I want to begin to talk about implicit differentiation. So the most important rule to understand is the chain rule for differentiating a composite function, or a very special case is the chain rule for powers. If we have a function g of x, and we raise that function to the pth power, and we take the derivative of the pth power of g of x, by the chain rule, this is p times g of x to the p minus first power times the derivative of g. So this is the product rule for powers that we use a lot. So if we had, for example, tangent of x plus 10, and we're raising that to the 21st power, what is the derivative? Well, my function g of x that we're raising to a power is tangent x plus 10. So this is when we apply the power rule, and the power p is 21. So we get 21 g of x to the p minus 1, which is the 20th, g prime of x. So that's 21 g of x is tangent x plus 10 to the 20th power times the derivative. If g of x is the tangent plus 10, the derivative of the tangent is secant squared, and the derivative of 10 is 0. So this is tangent x plus 10 to the 20th times secant squared x times 21. And you can also apply the chain rule when you have a composite of more than two functions. Recall the chain rule for a composite of two functions. We write like this: the derivative of f of g of x dx is f prime evaluated at g of x times g prime of x. The derivative of, with respect to x, suppose we had three functions, f of g of h of x. This would be f prime evaluated at g of h of x times the derivative of g of h of x, which is g prime evaluated at h of x, times h prime of x. So the formula looks a little bit complicated, though you have to get used to it. And as an example, suppose we had the derivative with respect to x of the sine of e to the cosine of x. So here I have three functions. I have cosine of x, and that's my h of x. G of x is the exponential function, and f is the sine function. So by this iterated chain rule, this is the derivative of the sine, which is the cosine evaluated at e to the cosine of x, times the derivative of e, which is e, evaluated at h of x, e to the cosine of x, times the derivative of the cosine, which is minus the sine. So we get minus, let's put it in more civilized order, minus sine x e to the cosine x cosine of e to the cosine x. So this is chain rule. Any questions about this? I mean, a large part of the midterm will be a list of functions for you to differentiate. So you need to know how to do it. So if you look at some of the exercises in the text at the end of the section, number 69, we have the function, which is x plus 2, x squared plus 1, that product raised to the fourth power. So this is a composite of this thing raised to the fourth power. So the derivative dy dx will be 4, this raised to the power 3, times the derivative of this product. And now we have to use the product rule. The derivative of x plus 2 is 1 times the second factor, plus the first factor, x plus 2, times the derivative of x squared plus 1, which is 2x. So this is 4, x plus 2, x squared plus 1, that whole thing cubed, times this. And if you expand it out, you get x squared plus 2x squared, which is 3x squared, plus 4x plus 1. Any questions about this? Let's look at another problem that's interesting. So I'm looking in the text on page 199, problem number 101, and this has to do with a damped oscillator. So if something is oscillating, say it's something hanging from a spring and going up and down as a function of time, t, and let's say the vertical displacement is y, if it's just oscillating, it looks like that forever. So the amplitude of the oscillations never changes. If you have a damped oscillator, it oscillates up and down forever, but the amplitude of the oscillations is decreasing. So you might have an exponentially decreasing function like this, and your oscillator is going up and down with the same period, but the magnitude, the amplitude of the oscillations is decreasing and going to 0, right? So this is a damped oscillator. So if, for example, in a room, you had a weight hanging from a spring, and you pull the weight down and release it, it oscillates up and down. And in a vacuum, and if there's no friction, it would oscillate forever, up and down. But in an actual room where you have air molecules that restrict the motion, impede the motion of this weight that's going up and down, you have a damped oscillator. So it will oscillate, but it will eventually come to what looks like a stop, because it's the magnitude of the oscillations can't be seen anymore. So one equation that describes a damped oscillator would be where the height y, so this is a damped oscillator, where the height y at time t is given by, for example, function 10 e to the minus t over 2 cosine of pi t over 8. So this e to the minus t over 2 is an exponentially decaying curve. And the cosine is oscillating up and down from -1 to +1. When it's negative, this is minus, this would be something like 10 e to the minus t. When t is 0, this is 10, so it hits up there at 10. But you're oscillating, and when t is 0, cosine of 0 is 1, and e to the 0 is 1. So you have an oscillation that looks like that roughly. Again, since I have maple, why don't I just show you in maple what it looks like? So let me open my maple, share the screen with maple. Okay. So my function y is a function of t. Let me see if I can make this a little bigger. T goes to 10 times e, you write e is exp for the exponential function, e of minus t over 2 times the cosine of pi, capital Pi, times t over 8. Okay. So that is my function, and let me plot it. So suppose I want to plot y of t. All right, that's what it looks like, but I only want to really know what it looks like beginning at 0. So let's plot it, say, from t equals 0 to 16 to start. Actually, suppose on the same graph, I want to plot this exponential function. So we see what is containing it. Oops. Y of t. I need a curly bracket. Oops. Let's see. What am I missing? Oh, comma. Ah, okay. So just so we can understand this a little better, let me plot this. Oops. I have this twice, which I don't need. So let me plot it without the y of t. So this is just this exponentially decaying function and it's negative, and the cosine, the oscillation, will fit inside of here. So let me put that here. Yeah. So the green and the blue are the exponential curves, and the oscillation is inside. So maybe just so we can focus on them a little better, suppose I let just y go from -1 to 1. There we are. So here is this curve. It's hard to actually see the oscillations. Maybe I'll make this 32 and from 0.1 to 0.1. Well, even there, it's hard to see because this curve decays. So, it's too bad. Experiment with one other thing. Yeah. So here, the green and the blue are the exponential curves, and the red is coming down and up, and it's oscillating in there, but it's getting so small so quickly that it really dies out very fast. So the picture is extremely interesting, but okay. In any case, this is what this oscillation looks like roughly, except it decays to 0 very rapidly. And so this is the graph. And suppose we want to find the velocity. So we have y is 10 e to the minus t over 2 cosine of pi t over 8. So the velocity v, which is y prime of t, when you differentiate by the product rule, you get 10. The derivative of e to the minus t over 2 is minus a half e to the minus t over 2 times the cosine of pi t over 8. This is the product rule, plus 10 e to the minus t over 2. The derivative of the cosine of pi t over 8 is minus the sine of pi t over 8 times pi over 8. So I can factor out e to the minus t over 2. And what do I have here? I have minus 5 cosine of pi t over 8 minus 10 pi over 8, which is 5 pi over 4 sine of pi t over 8. So this is the velocity at time t of this oscillating object. So we want to compute and graph the velocity. So let me go back to Maple. Maple is great, so why not use it? That's the velocity. Sorry, that's the function. So the velocity is the derivative of y at t. Okay. So if you look, that's exactly, oops, I'm sorry. I have to share screen. So here's my function y, and I just inserted the derivative of y, which is the velocity. See if this works. So that's the velocity. Minus 5 e to the minus t over 2 cosine minus 5/4 e to the minus t over 2 sine of pi t over 8. And let me just put that in here. Suppose I plot d of y of t. So this is what the velocity looks like. And it's squeezed between this exponentially decaying curve e to the minus t over 2, but it goes up and then it comes down, right? That's what it looks like. So when is the velocity equal to 0? Let's see if Maple can do that. Oh, well, let me first do it first. Let me do it by hand first. So stop share. Okay. So this is the velocity, and we're asked, when is the velocity equal to 0? Well, the exponential function is never equal to 0. So this is equal to 0 when this equals 0. So this equals 0 if and only if 5 pi over 4 sine of pi t over 8 equals minus 5 cosine of pi t over 8. And the 5's cancel. And sine over cosine, I can divide by that. So this is the same as sine over cosine, which is the tangent of pi t over 8, right? That's sine pi t over cos over 8 over cosine pi t over 8. And that's equal to minus 4 over 5. So the velocity is 0 at times that satisfy this equation. And remember, the oscillation is given by y equals 10 e to the minus t over 2 cosine pi t over 8. And when do you have local relative maxima and minima for this? When does this have reach its highest and lowest values? I guess we have to really just look at the curve. So so what's going to turn out, it's hard for me to do this without talking about maximum and minute too much. But the oscillation, this damped mass oscillating on the spring goes down and up and down and up and down and up. And you have these places where you have these relative minima and relative maxima. And those places occur exactly where the derivative of the function is 0. And the derivative of the function is 0 precisely where the tangent of pi t over 8 is minus 4 over pi. And That's really all there is that I need to say about this. Okay. Let's get to the topic of the day, which is implicit differentiation. So this is an extremely important application of the chain rule. So by implicit, we mean the opposite of explicit. So what does it mean? What is explicit differentiation? Explicit differentiation is when we have a function y, some function of x, y equals f of x, given explicitly, and we want to find dy dx, or f prime of x. So for example, if y is equal to x squared, dy dx is 2x. So here we have y given explicitly as a function of x. Or suppose y is the square root of 1 minus x squared. If you were to graph that, first of all, this is only defined when what's under the square root sign is non-negative. So 1 minus x squared greater than or equal to 0 is the same as x squared less than or equal to 1, which means x is between minus 1 and plus 1. And so the domain of this function, where this function is defined, is a function of a real variable with real values. It's defined for x between minus 1 and plus 1. And the graph is just the top of circle of radius 1, the semicircle. That's what this function looks like. And in this case, what is dy dx? So y is 1 minus x squared square root. So this is the derivative with respect to x. I can write this as 1 minus x squared to the power of half. Square root of something is that thing raised to the 1/2 power. So we can use the power rule. In the chain rule, this is 1/2, 1 minus x squared, a half minus 1, times the derivative of 1 minus x squared, which is minus 2x. These 2's cancel, and this is 1 minus x squared to the minus a half. I get minus x over the square root of 1 minus x squared. So that's the derivative. If we had the function y equals minus the square root of 1 minus x squared, the graph of that would be the bottom half of the unit circle. And in this case, dy dx, when I differentiate, it's the derivative minus this to the 1 minus x squared to the 1/2. So I would get minus x over the square root of 1 minus x squared. Minus times minus is plus x over the square root of 1 minus x squared. Right? So that's explicit differentiation. What does implicit differentiation mean? Well, suppose we look at the circle as the graph of the equation x squared plus y squared equals 1. That's the circle. And I'm not solving explicitly for y, it's just that this is the graph of the circle, and every point on the circle satisfies this equation, and every point that satisfies this equation is on the circle. If I take a point x, y on this circle, around that point, y is some function of x. So I take a point x, y, where x is strictly between minus 1 and plus 1. So there's some function, I haven't been told exactly what it is, but there's some function of y described by this curve. So if I call this function, whose graph is this little bit in red, y of x, for points on this curve, we have x squared plus y of x squared equals 1. So let me differentiate this with respect to x. The derivative of x squared is 2x. By the chain rule, the derivative of y of x squared is 2 times y, or y of x, times y prime of x. But that's all equal to the constant function 1, and the derivative of 1 is 0. So if I can solve for y prime of x, I get 2y, y prime is minus 2x. Divide by 2y, I get y prime is minus x over y. So at any point on this circle, except at the endpoints, minus 1 and 1, but at any point on the top and bottom of the circle, the curve is defined implicitly by a function of y. There's some function of y that's being satisfied by, for which this is the graph of the function. And differentiating by this trick, if you like, even though I might not know what y is, I found the derivative of y. So here's some more interesting examples. Suppose I have a curve which is defined by the equation sine of xy equals x squared plus y. So it's actually extremely hard to figure out by hand what the graph of this is going to look like. But I'm curious, so I'm going to use Maple to graph this. So let me go back to Maple. Share screen with Maple. Share. Here we are. So there's a command called plots. So with plots. Oops. This should be, let me do this correctly. With plots. If you're using Maple in your Math 155 class, you'll do this if you haven't yet. And if not, you can just appreciate the fact that I can do it. So I want to plot the curve given by this equation, sine of x times y equals x squared plus y. Let me just give a range of values for x and y. Say x goes from minus 10 to 10, and y goes from minus 10 to 10. I'll just start with that. Ooh, look at that curve. That is the graph of this function. So all the points on this weird curve look like that. Let me go down a little bit further. I'm sort of curious to see what this looks like. Wow. So this strange curve, quite fascinating, really. That's the graph of this function. And at almost any point on this curve, that a little arc of the curve will be the graph of some function. But I can't solve this. This equation is too complicated. I cannot solve it for y in terms of x. I just can't, I don't know how to do it. So that's what the graph looks like. Some weird thing like that. Interesting. But what I want to do, at any point on that curve, I want to find the slope of the tangent line. So I want to find the derivative of y with respect to x. So what I want to do is differentiate with respect to x. So for example, the derivative with respect to x of the right-hand side x squared plus y. That's the derivative with respect to x of x squared plus the derivative with respect to x of y. The derivative of x squared with respect to x is 2x plus what I'm trying to find out, dy dx. That's this. But this is the same as the derivative with respect to x of the sine of xy. And by the chain rule, that's the cosine of xy times the derivative with respect to x of xy. So that's the cosine of xy. The derivative with respect to x of xy by the product rule is the derivative of x, which is 1 times y plus x times dy dx, the unknown. So I actually have an equation. I can solve for dy dx. I have 2x plus dy dx equals this. Cosine of xy times y, or y cosine xy, plus x cosine of xy dy dx. And I can take this equation and solve for dy dx. And whenever I get, that's what I get, but we can solve for it. Okay. Let's look at a nice, somewhat more geometrical problem. Find the tangent line. That means find the equation of the tangent line to the curve x squared plus xy minus y cubed equals 7 at the point 3, 2. Let's just check one thing. Does this point lie? So this is some curve. Does this point lie on the curve? If you let x equal 3 and y equal 2, we get 3 squared plus 3 times 2 minus 2 cubed. That's 9 plus 6 minus 8. That's 15 minus 8. That is 7. So it checks. This point does lie on this curve. At any point on this curve, what is the derivative? So we want to find dy dx by implicit differentiation. So if I differentiate with respect to x, the derivative with respect to x of x squared plus xy minus y cubed, that's the derivative. I'm going to do this in several steps, but you don't have to do this with all these steps if you can do it with fewer. It's the derivative of x squared plus the derivative of xy minus the derivative of y cubed. The derivative of x squared with respect to x is 2x. By the product rule, the derivative of xy with respect to x is the derivative of x, which is 1 times y, plus x times dy dx, minus the derivative of y cubed with respect to x. By the power rule, this is 3y squared dy dx. So what I have is 2x plus y plus, I can factor out the dy dx, x minus 3y squared dy dx. That's the derivative of x squared plus xy minus y cubed. But that's always equal to 7. This is exactly the same as the derivative of the constant function 7 and the derivative of a constant is 0. So I have this plus this equals 0. So if I bring this over to the other side, I have minus x minus 3y squared dy dx, which is the same as 3y squared minus x dy dx equals 2x plus y. So dy dx at any point on the curve is 2x plus y over 3y squared minus x. So at any point on the curve, the derivative, which is the slope of the tangent line, is this. And I want to find the value of the derivative when at the point 3, 2. So when x is 3 and y is 2, this is 2 times 3 plus 2 over 3y squared. 2 squared is 4 minus 3. So this is 6 plus 2 is 8. 12 minus 3 is 9. So at the point on the curve 3, 2, this is the slope of the tangent line. At the point 3, 2. So what is the tangent line? It's the equation of a line with slope 8/9 going through the point 3, 2. So that's y equal to the slope 8/9 times x minus 3 plus 2. So that's 8/9 x minus 3 times 8 minus 24 over 9 plus 2, which is 8 over 9x. 2 is 18 over 9. See, 24 over 9 is the same as 8/3. Minus 8/3 plus 2 is minus 2/3. So if everything is correct, this is the equation of the tangent line. So let me switch to Maple and see what this actually looks like. Before I do, are there any questions about any of the calculus here or the algebra here? I mean, this is exactly the type of problem that should be on the midterms, right? Find the tangent line to a curve with either explicit or implicit differentiation. Okay, so let me share the screen again with you. So I have a certain curve. What was the curve? X squared plus x times y minus y cubed equals 7. That's my curve. Let me give it a name. I'll call it C, just so I don't have to keep writing it, but maybe I don't need to do that, but that's my curve C. And what does this curve look like? Let me plot the curve. I'll just choose some numbers at random and maybe modify it if I have to. So that's what my curve looks like from -6 to 6. That's my curve. If I want it drawn to scale, I can right click and go to scale and constrain. So that's really what this curve looks like. And I want to find the tangent line at the point 3, 2. Let me just check to make sure that this really does suppose I want to substitute x equal 3, y equal 2 into the expression this. I get 7. So this means when I put x equal 3 and y equal 2 into this expression, I do get 7. So the point 32, 32 is right about there, does lie on the curve. What's the derivative of this? Let me see. Let's try something. Implicit diff. Let's try it like this, see what happens. Oops. Let's see how implicit diff works. If you're using Maple in Math 155, it's very good to be able to use the help function. So implicit diff yx. I know what happened. Let's try this. There we are. Yeah, that's the derivative. And so in this derivative, if I substitute x equal 3, y equal 2 into this expression, I get 8/9. This is, slope of the tangent line at the point 3, 2. So what is the equation of the tangent line? Let me just give it a name. I'll call it tangent line. The tangent line is given by this number times x minus 3 plus 2. Oops. Don't know why that's there. Times x minus 3, that's missing. Perfect. Exactly what I got before. This is my tangent line. So let me go back to my curve and plot the curve and y equal tangent line. Oops. Okay, let's take one more careful look at this. So that's my curve C. And I want to plot that with the tangent line. I'm just going to write it out to make it easier. Oops. Ah, there we are. Okay, perfect. So here you see the curve. This is the 0.23, and there's the tangent line. So we found the tangent line to this curve. The curve was defined implicitly by this equation, sorry, this is the curve. The function y is defined implicitly by the equation. With implicit differentiation, we can find the derivative. From that, we can compute the tangent line. And here is a lovely graph of it. Right? That's really very, very, very nice. All right. All right, that is implicit differentiation, and let me do a few more examples of this because this is an important technique to learn. And when you're taking the exam in school, you're not going to have a computer to rely on or a calculator. It's just pencil and paper. And yeah. So I'm going to look at some of the problems at the end of the section 3.8 on implicit differentiation. Here's number 46. We have a curve given by x cubed plus y cubed equals 2xy. And you can check the 0.11 satisfies this equation because when x and y are 1, on the left you get 1 cubed plus 1 cubed, and on the right you get 2 times 1 plus 1, and this simply says 1 plus 1 equals 2. And the graph of this looks something like that. And this right here is the 0.11 on the curve. And we want to find the equation of the tangent line to the curve at that point. So first we have to define the derivative by implicit differentiation. If we take this curve and we want to differentiate with respect to x, the derivative of x cubed is 3x squared. The derivative of y cubed with respect to x is 3y squared dy dx. The derivative of 2xy with respect to x by the product rule is 2y plus 2x dy dx. So we get an equation that looks like that. If we rearrange it, we have 3y squared dy dx minus 2x dy dx equals 2y minus 3x squared. From this, we can factor out dy dx, and we get 3y squared minus 2x. So dy dx is equal to 2y minus 3x squared divided by 3y squared minus 2x. So with implicit differentiation, this is dy dx. And we want to know the value of the derivative at the 0.11. So dy dx at the 0.11 is equal to, when x and y are 1, 2 minus 3 over 3 minus 2, which is minus 1. So that's the slope of the tangent line. So all we need is the equation of the line through the 0.11 with slope minus 1. And that equation is y equals minus 1 times x minus 1 plus 1, which is minus x plus 2. So y equals minus x plus 2 is the solution to the problem. Okay. Now, it's also important to know what the normal line is. So we show lines the normal line to a line L at some point P on the line. So here's the line L. Here's a point P. The normal line is the line through P perpendicular to L. So the normal line to a line L at a point P is the line through P perpendicular, which is also normal, they're synonymous. The line through P perpendicular to L. So if line L has slope M, then the normal line has slope. So if you don't know this from pre-calculus, now I'm telling you, and so now you have to know it. It's the negative reciprocal of the slope, minus 1 over M. So if a line has slope M, the line perpendicular to it has slope minus 1 over M. The only problem is when M equals 0. If M equals 0, the line is horizontal. In that case, the normal line is vertical. So, and you could think of the slope of a vertical line as being infinite, but so let me just say, if a line L has slope M different from 0, then the normal line has slope minus 1.
Thank you.
Okay.
Wait.
Any questions about that?
Oh.
Okay. So let's do an example where we have to find a tangent line and a normal line. So what will be a nice example? Let me take a nice example from the book. Say number 47. 47, we have the equation x squared plus xy plus y squared equals 7. And the point 2, 1, so this is my curve. And then I have the point 2, 1, because if you let x equal 2 and y equal 1, 2 squared plus 2 times 1 plus 1 squared is 4 plus 2 plus 1 is 7. So this point lies on this curve. How do I find the tangent line? I have to find dy dx by implicit differentiation. If I differentiate this with respect to x, the derivative of x squared is 2x. The derivative of xy is the derivative of x, which is 1 times y, plus x times the derivative of y, plus the derivative of y squared, which is 2y dy dx, equal to the derivative of 7, which is 0. So this says 2x plus y plus x plus 2y dy dx is 0. If I solve for dy dx, I get minus 2x plus y over x plus 2y. And if I evaluate that at the point 21, dy dx at x equal 2, y equal 1 is minus 2 times 2 plus 1 over 1 plus over 2 plus 2 times 1. That's minus 5/4. So the tangent line, I'll call it TL, is the line through the point 21 with slope minus 5/4. So that will be y equals minus 5/4 x minus 2 plus 1, or y equals minus 5/4 x plus 10/4, which is 5/2 plus 1, or minus 5/4 x plus 7/2. That's the tangent line. The tangent line has slope m equal minus 5/4. The negative reciprocal, minus 1 over m, is plus 4/5. So for the normal line, it'll have be y equals 4/5 x minus 2 plus 1. So that's 4/5 x minus 8/5 plus 1 minus 3/5. And let me graph this just so we can see that things are what they're supposed to be. So let me share the screen again with Maple. And get everything out of memory. And I want to be able to use plots. And implicit plot. What was my curve? X squared plus x times y plus y squared equals 7. And say I graph it from x equal to maybe minus 4 to plus 4. Oops. Oh, sorry. I need the y to, and x equals minus 4 plus 4. Y equals minus 4 to plus 4. There we go. So I have a twisted ellipse. It's quite lovely. And I'm going to be interested in the point 21, x equal 2, y equal 1. That's the point right there. But I calculated the tangent line. Just to make sure I did things correctly. If I use implicit differentiation, which means the command implicit diff, to differentiate this, y with respect to x, that's what I get for the derivative, which is exactly what I got when I did it by hand, which is reassuring. And the tangent line should be what? Well, by that x equal 2 and y equal 1, my slope is minus 5/4 times x minus 2 plus 1 minus 5/4 x plus 7/2, just what I got. And the normal line will have slope, the negative reciprocal of minus 5/4, which is plus 4/5, times x minus 2 plus 1. 4/5 x minus 3/5. And now, let's see what happens. Oops. Let's introduce these tangent lines. Let's see, maybe I can just do it here. So here is my curve. And I want to put y equal to the tangent line. Wow. So here's the 0.21. Let me draw it to scale. That's always interesting. Here's the 0.21, and that's the tangent line. And if I add y equal the normal line, fantastic. So here you see the normal line, and they are perpendicular. They're perpendicular because it's drawn to scale. I use scaling constrained. Otherwise, if you have different measures on the x and y axes, it wouldn't look perpendicular. But when you use scaling constrained, it will look perpendicular if it's done correctly. So here's my ellipse. On the ellipse is the 0.21. Here is the tangent line, and here is the normal line. Okay. Any questions about that? Okay. Let me just so let me end the stop share, and there's one more thing I want to do today, which is calculate some more derivatives. So more derivatives. We know that the derivative of e to the x is e to the x. And we also know that the exponential function and the logarithm are inverses of each other. If we take e to the ln of x, we get x. And if we take the log of e to the x, we get x. And we can use this to compute the derivative of the logarithm. So suppose I let y equal ln, the natural log of x. So we know that e to the y, that's e to the log x, is equal to x. So from x equal e to the y, I'm going to differentiate both sides with respect to x. So the derivative of x with respect to x is 1. And that's going to be the same as the derivative with respect to x of e to the y, which by the chain rule is e to the y times dy dx. So that means that dy dx is 1 over e to the y. And e to the y is equal to x. So 1 over x. So this gives us an extremely useful formula. Y is the natural log of x. So the derivative of the log of x is equal to 1 over x. That really is one of the most fundamental derivative rules in calculus. We know the derivative of x to the n is nx to the n minus first power. Derivative of the sine is the cosine. Derivative of e to the x is e to the x. The derivative of the log of x, and in calculus, the only logarithm is the natural log, ln. The derivative of the log of x is 1 over x. Of course, what does the graph of log x look like? It looks like this. This is y equals log x. It's only defined for x greater than 0. We also have the function log of the absolute value of x. So this is defined for x different from 0, because if x is negative, absolute value of x is positive. So the graph of the log of the absolute value of x looks like that. And if x is greater than 0, the absolute value of x is x. And so the derivative of log of absolute value of x is 1 over x. If x is less than 0, the log of the absolute value of x is the log of minus x. And the derivative with respect to x of the log of minus x is going to be 1 over minus x times minus 1, which is, again, 1 over x. So for the function log of absolute value of x, the derivative is 1 over x. This is positive if x is positive, and negative if x is negative. This is all done legibly and very nicely in the text. The only functions whose derivatives we don't yet have are the inverse trigonometric functions, the inverse sine, the inverse cosine, and so forth. And let me just show quickly, I'll go over this again on Wednesday, how we find the derivative with respect to x of the arc sine or the inverse sine of x, and the derivative with respect to x of the inverse tangent of x. The other trig functions inverses are done similarly. So to say that, and what is y equals sine inverse of x? What does this function look like? This is the same as saying the sine of x, sorry, the sine of y is equal to x. What is the graph of y equals the inverse sine of x? So the sine of x takes on values from -1 to +1. So we can ask, for every number between -1 and +1, x, what is the angle whose sine is that? So what is the angle whose sine is 0? It's 0. What is the angle whose sine is 1? Pi over 2. What is the angle whose sine is -1? Minus pi over 2. And the graph of the inverse sine of x is defined for x between -1 and +1. That's the graph of the inverse sine function. So if we apply implicit differentiation to the equation x equals the sine of y, the derivative with respect to x of x is the derivative with respect to x of the sine of y. The derivative with respect to x of x is 1. The derivative of sine y with respect to x by the chain rule is the cosine of y dy dx. So dy dx is 1 over the cosine of y. I'd like an answer in terms of x, y is a function of x, but we know that sine squared y plus cosine squared y equals 1. So cosine squared y is 1 minus sine squared y. So cosine y is plus or minus the square root of 1 minus sine squared y. Sine y is x. This is plus or minus the square root of 1 minus x squared. Ah. But which is the sign, positive or negative? Well, first of all, this is increasing, so it has to be positive, just from looking at the graph. So this is 1 over square root of 1 minus x squared. And that's the answer. You don't have to remember the proof, but you do have to know the result. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. So this is an important technique, and on Wednesday I will apply it to calculate the derivatives of all of the trigonometric, inverse trigonometric functions. Any questions about any of this? This is all kind of interesting and good. Okay, then I guess we're done for the day. It's supposed to snow tonight, so stay warm and dry and be back on Wednesday.